In this lecture, let us discuss the Z-transform. As we know, in the continuous time domain or continuous time signal, okay, so we have continuous time Fourier transform, right, and we encountered some difficulties, right. So the difficulty is like CTFT, continuous time Fourier transform for a continuous time signal is on the j omega axis, and there are signals for which the CTFT does not exist because it will not converge, the integration will not converge. Okay, so there are certain signals for which you cannot find out a continuous time Fourier transform. So for those signals, what you do is, instead of multiplying x of t by e to the minus j omega t, we also introduced a convergence factor e to the minus j sigma t. So e to the minus sigma t multiplied by x of t, and then you take the Fourier transform and dt. Okay, therefore, so that the resulting signal can be written as x of t e to the minus sigma t times e to the minus j omega t, and this you can simplify as minus of sigma minus j omega times t, and the sigma minus j omega t you called s, e to the minus st times dt multiplied by x of t and integral like this. Therefore, this e to the sigma t is called minus sigma t is called a convergence factor. So the signal which does not have the continuous time Fourier transform, for those guys you multiply this e to the minus sigma t, which is convergence factor, and then you can find out the transform. Okay. So in other words, the CTFT will exist for an appropriately chosen value of this sigma. You choose the appropriate value of sigma, and then you can find out the continuous time Fourier transform. So e to the minus sigma t is a convergence factor, and this gives rise to what is called a Laplace transform. Okay. So Laplace transform is in terms of the variable s, small s, that is any point in the s plane, that is from a one track mind we are now diversifying, we are covering the complete complex plane. So similarly, the Z transform has the same kind of interpretation. Okay. So how we moved from CTFT to Laplace transform, in the same way we can give the interpretation from DTFT to Z transform. So the Z transform also has the same interpretation as the Laplace transform. Okay. That is, there are sequences x of n for which the DTFT does not exist. We have seen some couple of examples. Okay. So what we do is, instead of multiplying, what is the DTFT formula? Summation of x of n e to the minus j omega n, right. So you are multiplying x of n with e to the minus j omega n, and you sum them up, n is equal to minus infinity to plus infinity. So instead of multiplying simply by e to the j omega n, you take x of n first, multiply by some convergence factor, let me call it r to the minus n, and then you multiply e to the minus j omega n, and then sum them up, n is equal to minus infinity to plus infinity, and this r to the minus n is called a convergence factor for discrete time signals, and this transform is called, now it is called a Z transform. Okay. So in DTFT we compute on the unit circle, because this r to the minus n is assumed as 1, that is 1 to the minus n. We assumed r is equal to 1, r is the radius of the circle. Okay. Therefore r is equal to 1, which is unit circle. So in DTFT omega varies on unit circle. But in Z transform, omega varies not in the unit circle, but on the entire complex plane. So we are assuming that we are computing in the complex plane, but we are confining ourselves to the unit circle in DTFT. If you move this restriction r is equal to 1, now if you want to go to the general Z plane, then what we do is the following: summation of x of n, you combine this r to the minus n and a to the minus j omega n as r e to the j omega whole to the minus n. So we introduced a new variable which can now encompass the total Z plane because of this small r. The small r can vary from 0 to infinity. In DTFT, small r, this is for Z transform r. In DTFT, r is equal to 1 in DTFT. Therefore, in DTFT, small r was restricted to be equal to 1. In Z transform, the small r can take any value, and therefore, if you introduce the symbol z, let me put small z for r times e to the minus j omega, and this expression may reduce to summation of x of n z to the minus n, and the lower limit is minus infinity and the upper limit is plus infinity, and this is denoted by capital X of small z. Okay, this is called a Z transform definition. Okay, let me put the triangle symbol here. So this is the formula for Z transform. So the formal definition is capital X of small z is equal to summation of x of n multiplied by z to the minus n, and where the lower limit is minus infinity, upper limit is plus infinity. So this is the generalization of the DTFT. Z transform is the generalization of discrete time Fourier transform. Okay, but the properties are quite different. Okay, they are not very similar. Like small z, as you realize, is a continuous variable. Okay, the small z is a continuous variable. Therefore, this guy has magnitude and this guy has angle omega. Okay, the magnitude is r and the phase angle is omega. Now you also notice this x of z is equal to summation of x of n z to the minus n, and yeah, now look at here, this is nothing but okay, let me write down here, this is summation of x of n r to the minus n e to the minus j omega n. The same Z transform I can write like this, and now let me call this x of n times y of n as r to the minus n as some other name y of n. So this is nothing but DTFT of not x of n but x of n multiplied by r to the minus n. Okay, so I can write Z transform of x of n is equal to discrete time Fourier transform of x of n multiplied by r to the minus n. Okay, so therefore the Z transform can also be looked at as the discrete time Fourier transform of the sequence x of n times r to the minus n. So I can say Fourier transform, discrete time Fourier transform of x of n times r to the minus n. So this is another way of looking at it. And naturally the question of existence comes. Now the question is, does it exist? Because in DTFT we need to make sure that whether the convergence occur or not, whether it exists or not. Okay. or does it not exist? Obviously, one of the sufficient condition, if you recall, would be that the new sequence x of n times r to the minus n have artificially, this r to the minus n is artificially introduced, and this new sequence has a convergence factor r to the minus n. Now you have to see whether this x of n times r to the minus n is absolutely summable or square summable. Absolutely summable or square summable, that you have to make sure. That is one important point. If it is neither absolutely summable or nor square summable, you can't definitely say whether Z transform exists or not, because both absolute summability and the square summability are sufficient conditions. Okay. If it is neither absolutely summable or nor square summable, you can't definitely say whether Z transform exists or not, because both absolute summability and square summability are sufficient conditions. They are not necessary and sufficient conditions. This also complicates matter, because in discrete time Fourier transform we are only concerned with the one track, a circle of radius r is equal to 1. Okay, now we are expanding it to the total Z domain, total complex frequency domain. So r is equal to one circle, 1 unit circle to total Z domain. I mean total complex frequency domain. Okay, and therefore we will have to consider the question of existence in terms of what is known as ROC, region of convergence. Region of convergence, that is the place where the sequence will be converged. If the sequence does not converge anywhere in the Z plane, I mean if the summation of x of n times z to the minus n does not converge anywhere in the Z plane, then you say Z transform does not converge. Okay. If the sequence x of n times z to the minus n does not converge anywhere in the Z plane, then you say that the Z transform does not exist. Okay. So, the other conclusion that we can draw is that if the region of convergence of Z transform includes the unit circle, this is my unit circle, then the DTFT will also exist. Okay. If ROC includes the unit circle, then the DTFT will also exist. If it does not include, then you can't say that DTFT will exist or not. I mean it can't exist. So, the region of convergence is a region where the Z transform exists. Therefore, ROC, region of convergence, is a region where the Z transform exists. If the ROC includes unit circle, then its DTFT will also exist, but vice versa is not true. If the ROC includes the unit circle, then you can't say that Z transform exists. Okay, the DTFT may exist, but the Z transform may not exist. Okay, in DTFT we wrote the transform as x of e to the j omega. In Z transform we will write x of small z. Okay, with the magnitude of z equals 1. Okay, you must add or provided if ROC includes mod of z is equal to 1, not simply z equal to 1. Okay, so x of e to the j omega is the same as capital X of z, provided mod of z is equal to 1. Okay, so that's all about the introduction of Z transform. Now let me take a couple of examples. Before we take the example, let me just make a statement and then I will illustrate it later. So let's say g of n is a discrete time domain sequence, and then you take Z transform, you will get g of z, capital G of z, which is Z transform of g of n. If g of z, which is the transform of g of n, exists, this if g of z exists, then the region of convergence in general is an annular region. ROC is in general an annular region. Okay, and this annular region is bounded by two circles. One is inner circle and the other one is outer circles, and this region is called the annular region. Okay, and let me call the radius of the outer circle as r suffix L, and the radius of inner circle as r suffix R. In general, the ROC lies between two circles of radii RL and r suffix R. The significance of the subscript will be clear a little later, but if it does exist, okay, if ROC exists, it exists in an annular region. This region is called the annular region. Obviously, it will exist if r suffix small r is less than r suffix L. Okay, if r suffix r radius is less than r suffix L, then only it will exist, not otherwise. And this RL can go up to infinity. Similarly, okay, r suffix L can extend up to infinity. Okay, so RL may be up to infinity, and similarly r suffix R can be as small as possible, and this will be as big as possible. As small as possible means the sense r suffix R can go to 0 also. Okay, so it can be as small as the origin, that is 0. Here 0 indicates origin, it can include the origin, very very small, infinitesimally small. Okay, we will find examples in which our RL can go to infinity, or r suffix small r can go to 0, or it can be a region between infinity and 0. Okay. Now let us take some examples to illustrate this fact. First, take the simplest example. X of n is equal to del of n. So the question is, what is the Z transform of del of n? By definition, x of z is equal to summation of x of n z to the minus n, and the limit is minus infinity to plus infinity. But but del of n exists for n is equal to 0 only. So this is equal to 1. In other words, the Z transform of del of n exists at all values of z. Okay, it is independent of z. In other words, all values of z means what? R suffix r is 0. I can't put tends to, it is 0. And r suffix l is infinity. Therefore, the ROC is total z plane. Okay, so x of z is equal to 1 for all z. Now example number 2, x of n is equal to u of n. What is x of z? X of z equal to sigma by definition minus infinity plus infinity x of n times z to the minus n, but this u of n exists from 0, therefore the lower limit is 0 and upper limit is infinity, and u of n is 1 in this range, z to the minus n. Okay, because the sequence starts at 0, starts at n equals 0. If we expand this, this is going to be 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3 and so on and so forth. It goes up to infinity. So this is a geometric progression. Geometric progression, and the sum is 1 divided by 1 minus z. 1 minus z to the minus 1, provided that this z to the minus 1 is take modulus and that must be less than 1. Okay, this z to the minus 1 is restricted to be less than 1, otherwise you cannot sum it up. And how do you simplify this? 1 by z is less than 1 and 1 is less than mod of z, that is your region of convergence greater than 1. This is my ROC. So x of z equal to 1 divided by 1 minus z to the minus 1, or you can write x of z equal to z divided by z minus 1, but ROC is mod of z is greater than 1. So how do you plot this? You draw a unit circle with the radius 1 unit. ROC is outside the radius of 1 circle. Okay, so the ROC in the z plane is outside the unit circle. This is my unit circle. The total region of convergence outside the unit circle. Okay, so the region of convergence is the total region outside of the unit circle. In other words, here r suffix r is equal to 1 and r suffix l becomes infinity. That's it. You can do the same exercise. X of n is equal to minus alpha times minus n u of minus n minus 1. Then also you find the same result, but in this case the ROC becomes mod of z is less than 1. You can work on it. Let me take another example. X of n is equal to alpha times n u of n. Okay, now u of n is multiplied by alpha n. So we took, instead of 1 times u of n, I have considered alpha to the n times u of n. So in a similar manner you can show as follows. X of z is equal to summation of alpha to the n u of n z to the minus n, and the limit is minus infinity to plus infinity. Since you have u of n, the sequence starts at n is equal to 0. Summation of alpha times z to the minus 1 whole to the n. Again this is geometric progression. So this is 1 divided by 1 minus alpha times z to the minus 1, provided mod of alpha times z to the minus 1 is less than 1. Okay, now simplify this. Alpha divided by z mod of modulus must be less than 1, therefore mod of alpha is less than mod of z, that is mod of z is greater than mod of alpha. So therefore the region of convergence is 1 divided by 1 minus alpha times z to the minus 1, and mod of z is greater than mod of alpha. That is, the region of convergence is you draw a circle with a radius alpha and outside the circle with a radius alpha. So instead of unity, the radius becomes alpha. So instead of the unit circle, we have to take a circle of radius magnitude alpha. Okay, only then the Z transform exists. In a similar manner, I can find out the Z transform of x of n is equal to r to the n cos of n omega naught. What you do is, you write cos n omega naught as r to the n e to the j n omega naught plus e to the minus j n omega naught divided by 2. You multiply u of n here, and here also you multiply by u of n. Then your sequence becomes r to the n e to the j n omega naught by 2 u of n plus r to the n e to the minus j n omega naught by 2 u of n, and you separately find out the Z transform of this guy first term and find out the Z transform of the second term and add these two Z transforms. If you do this operation, you will get r times sin omega naught z to the minus 1 divided by 1 minus 2r cos omega naught z to the minus 1 plus r squared z to the minus 2. So this is r to the n cos of n omega naught and u of n Z transform. So straight away I wrote the result. You can work on it and you can prove that. Similarly, you can find out r to the n sin n omega naught and u of n. This also you can do it. You can find out what it is. Okay. So let me stop at this point and we will continue from here in the next lecture. Thank you very much.